Basic 40 grammi, ok?
Okay. So last week we were concluding physical processes. We have discussed mass transport and mass balance along the horizontal and among the different ecospheres. Today, we shall go to more on detail, because in a world in which there is a dominant direction, that is the vertical direction due to the gravitational force, we shall describe now how vertical movement may be treated by mathematical models. So on last lecture, we have seen horizontal movement through mass balance, mass transport. We have seen ecological processes, physical processes in terms of advection and adsorption. And today, instead, we are going to look in details how we can model settling and resuspension, that is the vertical movement of substances as customary in water ecosystems. We will also discuss briefly energetic factors like solar radiation and temperature, and we will give a look into the nitrogen cycle. But as you are environmental engineers, you may understand that nitrogen cycle is a key cycle to understand in order to manage ecological quality in ecosystems. So let's start looking at how we model vertical movement, settling, and resuspension. In the aquatic environment, with physical processes that determine the transport from the water column, for example, phytoplankton settling out from the aquatic zone to the benthic compartment and vice versa, are the so-called settling processes. The reverse of the settling process is the resuspension. So the vertical movement from the bottom of the water ecosystem to water column of material. In air, we talk of deposition and erosion due to the wind. We will not talk of these factors because they are quite complicated factors that need a specific treatment. But we are, as I have introduced in general, we look at water ecosystem. This is why today we shall look at settling and resuspension into aquatic environments. The basic hypothesis on which all these models are constructed are that of non-interacting particles. This means dilute solution, non-aggregated particles, and this hypothesis it is not always true. For example, as you know, as environmental engineer, often in wastewater treatment plants, the hypothesis, for example, of non-aggregation or dilute solution is not always acceptable. This is why under certain conditions, the settling models or settling process need to be treated specifically for wastewater treatment plant. In general, we start from the Newton's second law, in which we say that the force mass times acceleration is equal to the resulting vectorial sum of the various forces acting on a particle. So we look we schematize a particle in a water system like this one, and on this particle we may imagine that there are three forces attacked. The first one is, of course, the gravitational forces that tends to push the particle downward. The second is the frictional force, opposites to this movement, and the third one is the buoyancy force, or the Archimedes principle force of buoyancy for these particles. I'm sure you have already seen this derivation, in particular for the gravitational force. Force due to gravity, we may write that the density of a particle times the volume of a particle times the gravity acceleration z is equal to the gravitational force, or to force due to gravity. On the contrary, for the buoyancy force, we may write that the density of a fluid times, again, the volume of a particle times the acceleration of gravity g is equal to the buoyancy force. And on the contrary, in particular for frictional forces, we may write that the drag coefficient times the surface opposite to the movement of a particle times the density of the fluid times the square of the velocity of movement divided by 2, which is the frictional force. Please note that frictional forces, as you may remember, depends on the square of velocity or speeds. If we put all these together and we assume that we are in steady state, meaning that the derivative in time of the speed of setting speed is equal to 0, so this is the steady state assumption. We put all these together, we obtain this expression for the speed of setting. This is the classical derivation of the setting speeds that you may have seen when you were discussing Stokes laws, in particular for spherical particles, or for those particles in which there is a fixed relationship between the volume and the surface opposed to the movement of a particle. This relationship reduces to this one, so the speed, setting speed, is equal to the square root of 4g gravitational acceleration times the difference between the density of particle and density of fluids times the diameter divided by the drag coefficient and the density of fluid. This equation is derived by the first one by assuming spherical particles. Is, of course, assuming spherical particles as a consequence a fixed relationship between the volume and the surface opposite to movement of a particle. In particular, we have seen that this relationship depends on the drag coefficient CD. What is the drag coefficient? You may recall the drag coefficient is a coefficient describing the condition of the flow, and in particular, I recall you these graphs that I'm sure you have seen already elsewhere, and these graphs displays the values of drag coefficient as function of the Reynolds number. So drag coefficient is a coefficient describing the effect of flow on the movement of particle, and the effect of flow depends on the condition of flow. In condition of laminar flow, we have small Reynolds numbers, while in condition of turbulent flow, we have larger Reynolds numbers, and in particular for different shapes of the particle, or spheric or cylinders, we have slightly different relationships. In particular, we know that the Reynolds numbers may be made expressed as a function of the diameter times the density of the fluid times the speed, the setting speed of a particle divided by the viscosity, the viscosity of the fluid. Of course, there is a linkage between the density and the viscosity. All these factors depends on temperature. We hide this dependence, and in particular in the conditions of laminar flows and spheric particle, we may simplify the relationships between the drag coefficient and the Reynolds numbers. In this way, we may write that the drag coefficient in condition of laminar flow and spheric particle is equal to 24 divided by the Reynolds numbers. And by this assumption, we derive what is called the Stokes law, that you have already seen elsewhere, that says that the settling speed is equal to the gravitational acceleration of gravity divided by 18 times the viscosity of a fluid multiplied by difference between the density of particles and density of fluid multiplied to the square of the diameter of a particle. I assume that you have already seen these laws, in particular for all other shapes, like that may be of algae. We may introduce an equivalent radius or a correction factor that corrects the Stokes laws in this way, so that in the case of turbulent flow and cylinders, we assume that we are in condition of drag flow drag coefficient near to 1, so 10 to the 0, so we are here to the horizontal limit 1. And in this case, we may write that the settling speed is equal to 1.82 multiplied by the square root of the difference of the density of particle and fluid multiplied by the diameter of particle and the gravitational acceleration g divided by the density of fluid. So this is to show you how you can derive explicitly a law linking the speed, the settling speed of particles in the water column to the conditions in the water column. The conditions are described by the densities of particles, densities of fluid, viscosity, and diameters. Of course, all these conditions depends on the type of particle you are looking at and on the condition of fluids, in particular on the temperature. Of course, there are simpler empirical relationships which you may employ, in which there are no constants, and in which we assume a first-order kinetic for the settling process. In this case, we may write that the variation of the mass of a certain substance in the water column, dm over dt, is equal to minus s, the coefficient, that is the rate of removal by settling, multiplied by the mass. Rate of removal by settling may be explicitated as the ratio between the settling velocity and the depth of the system, h. In this case, of course, you know that the solution of this first order differential equation is an exponential decreasing model, and by employing the relationship with Stokes' law as we have just introduced, we may rewrite that the setting rate of removal by setting is equal to the difference in density of the particles and water divided by the viscosity. In particular, this is a graph showing you the relationship between the viscosity and the density of a particle and the temperature. In particular, the black line refers to viscosity, but is always decreasing. The gray line refers to density, and as you know, the highest value of densities for particles is at 4 Celsius degrees. And then after these 4 Celsius degrees, both viscosity and density tend to decrease. So there is a kind of competing tendency of decreasing density of water and decreasing or increasing viscosity of water, so that we may obtain some kind of abacus or plots like this one, linking the settling rate S to the temperature, and by this kind of graphs for different density of the particles, or less to more dense particles, we have this growing function with temperature, so that we may say that with increasing temperature, the settling rate or the settling speed of a particle will increase. This means that in condition of increasing temperature, the settling rate will increase as well. Please note that this is a question that I often pose. What is the dependency of the settling rate with temperature? And the right answer is that increasing temperature increases the settling velocity as well. The point of inversion, of course, is this one in which the two curves meet. So after this point, the viscosity tends to dominate, and this is why after this point, the density of the particles, in this case, this is the density of a particle, tends to increase as well. This is the process describing vertical movement of material from a water body, from a water column down to the sediment. The reverse process is called resuspension process, is the movement of material from the sediment to the water column. In this case, we have also model. What are the factors playing a role in this case? The wind energy is the first relevant factor. Wind energy that is translated into wind speed and the fetch. Fetch is the length over which the water, the length over which wind is allowed to flow the water body. So the longer the fetch, you will have an increase. The longer the fetch, the higher the wind speed, you will have a higher transfer of wind energy to the water body. Wind energy is transformed into waves. The waves are described by the speed of waves, the height of the waves, and the periods. Periods, of course, is equal to the length divided by the speed of waves. And then we have to describe the energy in water, but depends on the depth and the so-called shear stress tau. In particular, our models, the model we typically employ is schematized by this drawing. This is the surface of the water body. This is the wind blowing at a speed u. This is the length of the wave, and this is the height of the wave. This is the fetch, or the surface, the length of the surface of the water over which wind may blow. As a consequence of wind flowing on the surface of the water body, we have a formation of waves, and the waves generate a kind of cyclical vortex that starts large and becomes smaller and smaller. And when you go to the deeper part of the water body, you will have that the energy of the wind that is transferred to the water in form of waves is transferred to the bottom part of the water body in the form of shear stress. Shear stress depends, of course, on the depth and on the characteristics of the water system, water body, but the quantity of material that is moved from the sediment onto a water column depends on the sediment characteristics. How do we model this? We say that there is a critical shear stress tau c that depends on the sediment characteristics, for example, grain size, or the consolidation of quantity of water into the sediment. And when the shear stress, that is the translation of wind energy in water, as a force that I recall you, it is a vertical force pushing material from the bottom of the water body, so from the sediment onto a water column, is larger than the critical shear stress, that is a characteristic of sediments, then you will have resuspension material that is moving from a sediment onto a water body. Please note that the shear stress translates the energy of the wind through the waves and through the vortex induced by the waves, but while you are traveling toward the coast, so toward lower depths of the water body, then the effect of this force, of this energy is greater. So this vector, vertical vector, shear stress pushing upwards material from the sediment increases. So I recall you that we have said that there is another force, but it is the critical shear stress depending on the characteristic of the sediment. The critical shear stress, it is a vertical force as well, this times oriented toward the bottom. So it is a force describing the fact that material particles tend to stay aggregated into the sediment, while the shear stress, it is a vertical upward force. How do we model in detail this process? We may say that if epsilon is the quantity of resuspended sediments into the water body, we may say that the quantity of resuspended sediment is equal to 0 if tau, so the shear stress, is smaller than the critical shear stress, and when the shear stress becomes larger than the critical shear stress, then we have this expression describing the quantity of material resuspended. So the quantity of resuspended material from sediment is equal to these constants, alpha 0 and tau, and TD, times the difference between the shear stress and the critical shear stress, elevated to a power 3, the cube of this difference. Epsilon is generally measured in grams per square meters, while tau, that is a force, stress, shear stress, is generally measured in dine times squares, dine divided square centimeters, and customarily, the constants that appear into this model are this one: alpha 0 is equal to 0.008, and TD is equal to 7 dine, that is equivalent to 1000 newtons, more or less. We know that for shallow water systems, we may express the shear stress as a simple function of the speed of water. So we may write that the shear stress is equal to 0.003 to the square of the speed of water, but where at 15 centimeters from the bottom. Why 15 centimeters? Because exactly to the bottom, the speed of the water is 0. So by assumption, it is a customary assumption to say that we measure the speed of the water at 15 centimeters above the bottom, and by this measure, we may evaluate the shear stress by this model. In particular, for shallow water bodies, again, we may explicitate the value of the speed of water at 15 centimeters from the bottom by saying that the speed of the water at 15 centimeters from the bottom is equal to P times HS, that is, as you may recall, HS, it is the height of the wave, times 100 divided by the hyperbolic sin of 2p's divided by the depth of the water system and the period of the length, sorry, the wavelength of the waves. In particular, note that this very special model that is applicable for shallow water system simulates the wind, the effect of winds on the speed of water at 15 centimeters from the bottom, but does not simulate in any way the effect of currents. In particular, there is another interesting abacus that is very appreciated by environmental engineers that links the mean velocity at 15 centimeters above the bottom to the size, diameter, and so to the characteristics of the sediments in terms of size, diameter, that is the granulometry, but also in terms of consolidation, so in terms of water content, and for different water contents, 50%, 60, 70, 80, 90%, we have that at increasing size or increasing granulometry of the sediment, we have a tendency to increase the movement of material horizontally on the bottom. So we have transportation, that is horizontal motion on material on the bottom of the sediment. We have erosion, that is resuspension of material from the sediment onto water column, and we have a contrary process, that is deposition of material from the water column into the sediment. So with this kind of graphs, you may, for example, identify the characteristic of the sediment in terms of granulometry, draw a vertical line, and as a function of different water content, but of course depends on the condition of the type of sediment, what is, for example, clay, silt, or sand, or so on, and a different condition of the sediments, you have different relationships between the speed of the speed of the water at 15 centimeters, the granulometry of the sediment, and the consolidation, the water content of the sediment. These type of graphs are increasing. This means that are increasing diameter, fixed, for example, the speed at 15 centimeter, increasing the diameter, you will pass, for example, from condition of deposition to condition of transportation, that is a horizontal movement, to condition of erosion, that is resuspension, actual resuspension, movement of material from the sediment toward the water column. So this is vertical movement of material. The characteristics of sediments are very important in order to evaluate the effect of resuspension. This is the most complicated, model we may. Of course, it is not the most complicated in detail, but is the most acceptably complicated model to describe movement from sediment onto water column. So the reverse of the sedimentation process. Okay, this more or less concludes the description of material movement. We have seen that horizontally we talk about mass transport, mass balance via CSTR or via the diffusion advective equation that we have seen last week. And we have seen how to describe vertical movement in terms of Newton's law of gravity. So the resulting of the forces in a steady state condition is equal to 0 because the acceleration of movement is equal to 0. From this you derive Stokes' law, from this you derive settling speed, but then we may employ a more sophisticated approach to describe the resuspension process, what is the reverse of the settling process. Now, the physical processes. In order to conclude the discussion about physical processes, we need to discuss a little bit more on energetical factors. I recall you that all the energy that drives transformation to ecosystems on the surface of our planet are based on solar energy. So the solar radiation is the main energy source for ecosystems' primary production, forcing for many ecological processes like photosynthesis, photolysis, and meteorological processes, but also evapotranspiration and so on. We may write from quantum mechanics that the energy transported by solar radiation is equal to h times nu. H is the Planck's constant, nu is the radiation frequency that may be expressed in terms of radiation wavelength, by saying that the radiation frequency is equal to c speed of light divided by wavelength. So the Earth's surface, we have said, lowers the quality of the energy, so photons are absorbed in the visible and ultraviolet and are retransmitted in the infrared. I think that for now, this way of reasoning should be quite customary to you. Ecosystem, and in particular system, ecological system surface of our planet have the quality of transforming high quality energy coming from solar light, solar radiation into lower quality energy that we may call infrared energy. I recall you that the energy balance is closed, meaning that if you make 100 the quantity of radiation arriving on the surface, when we have immediately 35% of this radiation that is reflected by dust, gas, clouds, albedo, so this is the atmospheric processes of reflection. Of 19% of this radiation instead it is absorbed by atmospheric gases like ozone, steam, clouds, and so on, and 46% is absorbed by the Earth. Of this 46% absorbed by the Earth, we have a complete re-emission from the lithosphere onto the atmosphere, is 46%, and this then it is given back to the gases into the atmosphere. And I recall you that you have only a very small quota of this energy, just with 5%, that is responsible for atmospheric circulation. And this is related to the heat of evaporation and convection of fluid. So that if you sum 19 and 46, you obtain 65. So that in the troposphere, you have restitution of total radiation that has arrived to the planet. So in this way, we say that the energetic balance is closed. In particular, it is interesting to look at the different types of solar radiation in terms of wavelengths. And for example, we know that of the 1,360 watts per square meters, that is the solar constant today, arriving at the intermediate distance Sun-Earth, this radiation 9% is ultraviolet, 41% is visible, and the half, 50% is infrared. Of ultraviolet, we have a very refined subdivision in terms of effects. For example, for ultraviolet waves, whose wavelength is smaller than 0.12 microns, these are absorbed by gases like oxygen or gaseous nitrogen in the highest part of the atmosphere, the stratosphere. 4% of these quota are absorbed and reflected into the stratosphere, so the highest part. Partially, this energy is absorbed by ozone, and instead of this, the quantity of ultraviolet in the range 0.34, 0.40 microns, of this plus the visible quota, this is what reaches the Earth, so ultraviolet plus visible, this is equal to 46% of all the radiation that arrives onto the surface, and it is reflected after being used and degraded by ecosystem. So this is the quota, is 46%, partially ultraviolet and visible, is what it is used by biological systems and degraded in order to convert this energy into more sophisticated biological macrostructures. Of 50% infrared energy, this means wavelengths between 0.71 and 3 microns. This 50% is absorbed and reflected from CO2 and N2O, so that is nitrogen oxides. at 10 kilometers on the lower parts of the atmosphere, the so-called troposphere. And it is this quota, this 50% infrared, but it is responsible of the effect that is known as the greenhouse effect. So it is infrared radiation that tends to increase the temperature of at the level of the surface of our planet. We may measure solar radiation through different units, in particular, or using different currency. In particular, the most formal physical one is watts per square meters. I recall you these are the units of the solar constant. Or we may employ the British thermal unit, and this is a conversion factor between watts per square meters and British thermal unit. We may use the Langlays per day. So this is, I recall you, W is a flow. So this is a density of flow. Langley per day, again, it is a density of flow because we have calories per square centimeter per day. So these are all conversion factors you may employ to pass from one currency to the other one. And then you may employ, for example, kilocalories or small calories. I recall you that 1 kilocalories corresponds to 4,182 small calories, watts. And you may also employ, in particular when studying ecological system, the Einstein's per square meter per second. One Einstein is a mole of photons. A mole is 6.02 10 to the 34 photons. You may measure the quantity of energy in moles of photons per square meter per second. So this is a flow, a surface density flow of energy. Of course, Einstein's cannot be converted in the above unit because we do not, Einstein depends, on photons. So this unit is used in order to compute photosynthetic active radiation. That is, we may say that 9 moles of photons in the visible are necessary to fix 1 mole of oxygen. So in terms of photosynthetic activity, we measure the quantity of solar energy in moles of photons in the visible spectra to fix 1 mole of oxygen. So the effect of photosynthesis is oxygen fixation. So we cannot convert directly Einstein's because, of course, with this definition of mole of photons, not all photons are equal. Instead, in the photosynthetic active radiation definition, we consider those photons that are capable of driving photosynthesis, and these are, as we know, in the visible and some are into the ultraviolet range. So we may say that 9 moles of photons in the visible or ultraviolet range are necessary to fix 1 mole of oxygen. So this currency, the Einstein per square meter per second, is a measure of the density energy flow necessary to produce 1 mole of, to fix 1 mole, to produce 1 mole of oxygen. Then we may want to describe the effect of solar radiation, and we discover that the effect of solar radiation depends on various factors, essentially 2 factors that are the location on which the solar radiation falls in, so we may say the latitude, but also the period of the year what the solar radiation is considered. In particular, we know that at different periods of the year, the Earth is at different distances from the Sun. So we need some kind of explicit modeling in order to take into account this fact. So we introduce a new factor that is this photoperiod. The photoperiod that is a function of the days of period of the year and of the latitude of the position. the day is represented here by n, and the latitude is represented here by phi. And we may write that the photo period, so the quantity of a 24-hour portion of a 24-hour day in which you have solar light is maybe made equal to twice the arc cosine of the tangent of a latitude times the tangent of declination, and declination, solar declination, is the height of the sun over the horizon divided by 360. So this function, photo period, goes from 0 to 1, 0 in the in our hemisphere. 0 means, sorry, one moment, 1 second, please. 1 second, spare. Sorry, I'm back. Okay. Yes, the photo period that has a value of 0 in the our hemisphere in winter, and 1 in our hemisphere during summer. Of course, I mean the Arctic hemisphere. So the northern hemisphere of the Earth. During summer, we have, depending on the latitude, so depending on the solar declination, we may have a quantity of solar radiation that goes, percent quantity of solar radiation that goes from 0 to 1. 0 during winter and 1 during summer. And for the solar declination, we have this very detailed astronomical model. These are all astronomical models in which we may say that the solar declination, so the height of the sun over the horizon, depending on the day of the year, epsilon. So, sorry, depending on the yearly angle, epsilon, is a function of sinus and cosinus of a yearly angle, and the yearly angle instead may be made dependent on the day of the year, and by saying that on the 365 days, we have these relationships that links the yearly angle to the day of the year. We consider the first day of the year, the 1st of March, so that during the 1st of March n is 0, so we have minus 21 divided 365 multiplied by 360. And by employing this definition, we may immediately calculate that the absolute value of the product of the solar of the latitude, maximum latitude times the maximum solar declination are always smaller than 1, fortunately. So this tells us that this quantity is positive in the range of 1. Yes? Are you asking something? No. Okay, in this case, phi max, that is the latitude, is considered the latitude of a polar circle, while declination, delta max, is the solar declination, that depends on the place, but particular angle. So that for the maximum value of you see, sorry. Oh gosh. Okay. In this case, the maximum latitude, solar declination, sorry, delta is at the Arctic Circle latitude. So the combination of this maximum latitude times of this maximum solar declination is so that this quantity is smaller than 1. Then in Arctic polar circle, we have the maximum latitude is 66.5 degrees, so that we have again that this quantity is smaller than 1. So we have a quantity here that is smaller than 1, and you may recall that we are cosine of a quantity that is smaller than 1. It is in the range 0, 90 degrees, sorry, 0, 180 degrees, so twice 180 degrees, it is 360. So this quantity is a normalized way of measuring the quantity of solar light that happens onto a particular place of the Earth, latitude, in a particular period of the year, so the day of the year through the yearly angle function. These functions are obtained through astronomical models, so there is nothing much to know about that. This is astronomical observation, but may be translated into this kind of models. For higher latitudes, values of P can be also 1 or 0, depending if we are in summer or in winter. 1 in summer in our hemisphere and 0 in winter in our hemisphere, of course. The model that we have seen here may be plotted. This sinusoidal model may be plotted, and we obtain a plot like this one. In this case, we plot the quantity of solar radiation, quantity of density of solar radiation flowing in different periods of the year, depending of different latitudes. So this is 50-degree latitude and 25 degrees latitude. We have these different curves. It's nothing more than a graphical plot of these functions, of this sinusoidal function. In this case, we may write that solar radiation can be easily measured, and we may build a model that is based on regression on real data. So even if you do not have precise data concerning the quantity of radiation that is falling onto your planet, onto your ecosystem, then you can employ this sinusoidal model, that is a generalization of this model, again, sinusoidal model, and by this, employ these two parameters, A and B, by measurements of solar radiation, and by regression of real numbers or real data, you may obtain this kind of function that are plotted this way. Of course, this radiation is assumed to arrive on the system on a mean daily clear sky, which we may subdivide short wavelength solar radiation. Of course, depends on latitude and day of the year, and we may, in order to include the effect of clouds, introduce a term, a coefficient, that is the fraction of covered sky. So these plots are obtained in condition in which the fraction of covered sky is 0 in average or mean daily. In average, the fraction of covered sky is 0. You may understand immediately that this is not always the case, because the fraction of covered sky depends on seasons, and in particular depends dramatically on the seasonality on tropical latitudes. because we know that in tropical latitudes we have a rain season. For example, in Venice here, these are experimental measurements of solar radiation, and this is the regression interpolation obtained by the model, sinusoidal model that we have discussed. Why, for example, in Manila, the Philippines, that is a tropical ecosystem, the condition is slightly different because, for example, during normal season, non-rainy season, we have kind of sinusoidal behavior, while during the rainy season, in which there is a predominance of covered sky condition, we have these measurements. So we have a kind of flattening quantity of energy arriving onto the ecosystem. Of course, we may be more precise in terms of the description of the heterogeneous cloud cover over the year, and we do this by simply constructing a balance, an energy balance in terms of solar radiation. For example, if we call the net solar radiation arriving on the surface of a planet like Q in is equal of to a quantity in the short wavelength minus a quantity that is reflected in the short wavelength. So we are distinguishing the effects due to clouds for short wavelengths and long wavelengths, because of course short wavelengths are absorbed differently from long wavelengths by clouds. So we have a first terms that describe the short wavelength cloud effect minus the short wavelength reflection effect plus a long wavelength quantity of energy assumed as absorbed by clouds minus a quantity of energy reflected by clouds in the long wavelength range minus the BR, that is the heat emission from water, that is the black body radiation. The short quantity of the net short wave radiation, QSN, so the wave radiation subtracted cloud radiation, short wave radiation may be expressed by these two terms. So the short short radiation absorbed by clouds minus short radiation reflected by clouds as well, and the experimental relationship between this quantity is given by this and by this equation, and depends on the fraction of covered sky. I recall you that this is from 0 to 1 and represent how much clouds are in the, on the sky, multiplied by the quantity of short wavelength absorbed by clouds. So we have a relationships that is a first order derivative relationship between the short wave radiation absorbed by clouds and the net short wave radiation. For the long wave radiation, we have a slightly more complicated equations in which we have a dependence upon the square of the fraction of covered sky, and there is a dependence on the dry bulb air temperature, but is in Fahrenheit. And all these figures are expressed in watts per square meters. So we have seen that in case we want to model in detail the effect of solar radiation arriving to the surface of our ecosystem, we may employ models, but for example, for short time scales, for example, for daily time scale, we may say that the intensity of radiation, the radiation intensity at time t is equal to the radiation intensity arriving at day n, and I recall you that the radiation intensity arriving at day n may be calculated by these models, by the sinusoidal models. by employing exactly these regressions. So sinusoidal model depending on the yearly handle and on the two coefficient AB. So this IN is the quantity of radiation arriving on the ecosystem day N. In this case, the quantity of radiation arriving to the ecosystem days N divided by the photo period days N at latitude phi multiplied by these quantities is may be employed as a model for describing the effect of solar radiation or the quantity of solar radiation arriving to ecosystem when your model has very short time scales, meaning, for example, days or weeks. T is the hour of a day and can vary between 0.5 minus the half of a photoperiod and 0.5 plus the half of a photoperiod. So it's the day length normalized to 1. E is the radiation intensity, En is the mean daily radiation given by the equation that we have seen before. Okay. Let's see, if you don't mind, I would like to stop here today, and we will go back next Thursday by describing the biogeochemical cycles of nitrogen, and we will finish with physical processes. More in detail, we will give a look at the transfer of nitrogen to various processes. All these processes are processes that you have already seen here and there during your student career, so we're not going to lose too much time because I am assuming you already have seen these processes. Here is just a matter of putting all these processes in the correct framework in terms of physical energetical processes. Okay, if you do not have any question, now I stop here and I wait for your questions, or otherwise we'll see next Thursday.
Excuse me, Professor?
Yes,
I have a couple questions.
please.